Thank you for the introduction, and also thank you for the kind invitation to present our present our work on nanoelectromechanical switches here at this conference. So first, for a bit giving technology has seen exponential growth with varying devices going from mechanical to ever more integrated and ever more smaller devices. And nowadays, the integrated circuits as CMOS, as already pointed out this morning by the plenary speaker, is facing again challenges, and people are looking for new ways to overcome these challenges. And nanotechnology is, of course, the way to go, everybody thinks. And I would like to propose you the NanoElectroMechanical switch as a way to go, which at the same time is also a way back in time, because electromechanical computing has existed before. So in a different view of the global landscape, there are two major trends. One is miniaturization and ever more computing power, which is also called more, and which is what the CMOS industry is doing best. And the other part of information technology is concerned with getting information in and out. So it's sensors and actuators, it's RF and passive devices. And we see that the MEMS chip, just from the technology point of view, and shares many common points with this kind of applications like oscillators or sensing. But we think, and I try to show you this in this presentation, that MEMS switch can also add functionality to the CMOS. And we try to push the MEMS switch more towards the digital processing. Now to the outline of my talk. First, I will also go a bit into detail what is the actual problem of the CMOS technology and why the MEMS switch offers actually a solution to some of the problems. Then I will present you our new design for an in-plane mechanical switch, and also show you how to optimize this design and what are the scaling limits of this design. And from this, I also want to show you what we think is the fundamental limit of NEM switch technology. So how far can we actually go in reducing power? And what on top of the device, so more on the circuit side, what approaches we can take to further reduce the power in computation. And finally, I will end my talk with our experimental results on fabrication and electrical characterization. Now, today's CMOS, one of the challenges is definitely the power or energy challenge. So one thing is that the cooling becomes ever more expensive if the power density is so strongly increased. And this puts a fundamental economic limit. Then the second point is leakage power. And in modern architectures, leakage power can, or modern devices, leakage power can is as close in absolute values or almost half of the total power in a CMOS device. And this is of course problematic for a couple of specific applications like autonomous devices where the amount of energy is very low, which is even there to do computation, or exascale computing where we cannot build power plants just for the single computing and data centers. And that's where we are looking for new opportunities which cannot be solved with CMOS technology. In addition to these two, CMOS technology, NEMS technology can also offer additional benefits. For example, it can be made radiation hard, and it can withstand higher temperature than CMOS technology. And we think it's mostly suited for dormant devices and sensor networks where the amount of computing is not as big. The advantage of the NEM switch is best shown on this graph, comparing the switching characteristic. A MOS switch has a characteristic subthreshold slope, which in the ideal case approaches about 60 millivolt per decade. A MEM switch, on the other hand, has a characteristic which is much closer to an ideal switch with a very abrupt on-off characteristic. However, the MEM switch has a hysteresis, and we also need to think about this hysteresis and what it means in terms of energy consumption. Then, as said before, the radiation just from the working principle, soft error is much less of a problem, and we can tolerate a much harsher environment. Also, MEM switches can address both logic and memory function, which is an advantage and offers potentially a technology platform for many applications. And the fabrication of mechanical switches is rather simple, at least in principle. And this promises lower cost as shorter fabrication processes are possible. And overall, we think for these attributes, if we exploit them correctly, the NEM switch is really an excellent candidate for a next switch. Now, the requirements, of course, are quite severe. So one thing is the scaling. Obviously, users don't want big devices now that they have these very small CMOS devices. So scaling is important, and we think that size scaling is pretty much the same as with CMOS technology. The air gap, so especially if you use electrostatic actuation, however, is really important, and we need air gaps below 10 nanometer with rather high aspect ratios. So we think the way to go is non-lithographic definition for the air gaps. Then one of the major or one key reliability point is definitely the contact, where we need a lot more than 10 to 10 cycles. And to achieve this, we need a good understanding of the contact physics and contact modeling to understand what are the reasons for degradation. The resistance for mechanical switches in logic applications, however, is not that stringent, as it is sufficient to have an electrical delay which is much lower than the mechanical delay. So overall, we can tolerate 10 kilo ohm or even 100 kilo ohm in most applications, because the mechanical delay is rather large. And finally, of course, depending on the application, we also have requirements in terms of material, which would be inert and stable, and in terms of actuation voltage, which needs to be as low as possible. But at the same time, the switch needs to be robust and survive the given harsh environment. So there are different switch topologies which can be imagined or which are currently also under development. Out-of-plane switches where the motion is vertical to the surface, in-plane motion, often done with silicon on insulator substrates, and vertical topology, which promise further reduction of the footprint. In our work, we have concentrated on in-plane switches because they offer freedom of design and potentially symmetric layers, which helps to reduce stress issues. And on top of this, the fabrication process is based on silicon on insulator substrate, and this is advantageous because it gives us quite a simple fabrication. And also the silicon has a very good mechanical properties. Now, the easiest way to design a MEM switch is, of course, to draw a straight cantilever and just one air gap over the gate electrode and over the drain electrode. However, if this is brought into contact, we have a strongly non-uniform field with an extremely strong field here close to the drain. And this is, especially in scaled version, this field can be very problematic and can lead to failure. So we have thought about ways to avoid this, and what we came up with is an inclined electrode. So here we have the gap over the contact, and we incline the actuation electrode with respect to the direction of motion. And then we have this angle beta here, which we can use to design the remaining gap once the switch is closed in this specific direction. So we have a geometrical way to define the closed state gap. Now we can calculate the electrostatic field at pull-in for such a simple 1D model, and we see that if the angle beta is 0, then we need a very high voltage and very strong field. If the beta is 90 degrees, so the cantilever is flat, we get, of course, also a very high field because the gate is touching the switch. And in between, we have a sweet zone with a minimum at around 30 degrees, where we can get a controlled gap with a very low or a lower electrostatic field. And now this 1D approach can be combined with the cantilever, and this will result in a curved cantilever. And this curvature of the cantilever can be used to get an actual almost uniform distribution of the electrostatic field with only one single gap over both the gate and the drain electrode. And therefore we still have a simple fabrication process, but we have a much better control of the structure in the closed state. Analyzing this, we have done a bit of analytical analysis and also of ANSYS analysis. The curvature is of course a trade-off between size and robustness, and on top of just the curvature we also designed the hinge region, which gives us stiffness. We have to design a contact region, and the total size gives us also the pull-in voltage, so we can tune all the different parameters. Now looking at the analysis, here you see ANSYS simulations from a straight cantilever with ever increasing curvature down to a cantilever which is strongly curved. And we see that the pull-in behavior, so the electromechanical instability, disappears when we increase the curvature, and at the same time also the actuation voltage increases as we have to go through more and more points, and our displacement is less abrupt. So this has the advantage that we can design a switch which can be brought into contact very smoothly, so we don't have a crash on the contact tip at every actuation. In addition, this higher actuation voltage is not a penalty in terms of energy, as the capacitance which we need to charge is strongly decreasing. So here you see a plot of gate capacitance as a function of applied actuation, and you see that for a straight cantilever here in yellow, the capacitance at pull-in increases very strongly. However, if we have a curved cantilever, this on-state capacitance remains much lower. And looking at it on the energy is the red curve here on the right side, and we see that the energy at first decreases and then slowly increases again, and we have an optimum at around 0.2, but rather small variation. Also the mechanical energy, which is plotted here in black, does not vary, it does not depend on the curvature. However, the electrostatic field shown here in green is decreasing by more than a factor 4 when we increase this curvature. And this results in a much better robustness here shown in the breakdown of the switch onto the gate, which is increasing from something like 2 volt up to 10 volt. So we get a much larger operating window. And of course it's always a trade-off then about how big the curvature needs to be for a given application. Then we looked at the switch also about the scaling potential, and we looked at different hypothetical technologies going down to about 30 nanometer in critical dimension, which is shown here. And we have seen that the main parameters to reduce the energy is the stiffness of the structure and the gap. And to get below 100 attojoule of switching energy, we need an air gap which is as small as 5 nanometers. Note that we have kept in these structures the restoring force always bigger than 10 nanonewton, because we have seen from theoretical modeling that for metal-metal contacts, this is really the fundamental limit. Of course, to get to such small structures, we need lithography scaling, we need scaling of the gap, of the air gap, and we need a contact fabrication method which allows such small forces. And we have started this work on such structures using e-beam lithography, as shown here. However, we have not yet integrated the gap scaling with these structures. So why 10 nanometers? We have developed a model for a metal-metal asperity contact based on a constriction resistance. And as a result, we see that we can express the contact force as a function of effective mass, of electron density of the contact material, and of the resistance. And if we assume that we want on resistance in the order of 2 kilo ohm, and we have a rather good metal, we end up with a contact adhesion force in the order of 6 nanonewton. And this is already for a very small contact in the order of half a nanometer with a couple of atoms. If we plug in this equation on the contact force into a model of an electrostatic actuator, we then find that the minimum actuation energy is proportional to the contact force and also proportional to the air gap. Hence the reason for this aggressive scaling of the air gap. And we end up with switching energies in the range of about 120 electron volt. Adding some parasitic capacitance and trying to compare it to CMOS, we see that the MEMS switch is actually a bit better than CMOS technology, but overall it's about the same level. So the energy is quite comparable. The delay, of course, is much bigger. What is not shown here is that the leakage current, which is present in CMOS, is not present in a MEMS switch even at 3 nanometer. So on this part, we expect a huge advantage for the MEMS switch. Also, we can say that from the first equation, if we want good contact, so a low adhesion force, we need a material with low electron density and high effective mass. So basically a poor conductor, which will give lower adhesion force. On top of the switch itself, we can of course also work with the way we design logic. And there are different approaches. One has been presented in 2007, and the idea is basically to move part of the computation from the switch, from the electrical domain into the electromechanical domain. And this can help to build more compact gates with fewer components. A second approach is to replace again the static NAND as shown here, which is the same as this one, with a logic type that is called transmission gate logic, which is not used in CMOS technology, but which has been used before as in the electromechanical, in the time when the electromechanical computing was used. And then we can again express a NAND with only 2 components. Now, other than that, there is the dynamic logic, which can help to recover energy. And in CMOS, the dynamic logic is not that beneficial because there is leakage and people need a bleeder to sustain the voltage levels. And this partly destroys the advantage of the energy recovery. Now, in a MEMS switch, there is no leakage, and it's inherently stable with respect to noise. So it is a good candidate to build a dynamic logic. So let me now go to the fabrication efforts. So far, we have built most of our switches in 1-micron technology because it's simpler and faster for us. But we also try to make sure that the technology can be scaled later on. Technology is based on a SOI substrate with an oxide on top, on which we pattern to form the mechanical movable switch structure. Then we create platinum silicide on the sidewall. So we clean the sidewall, we evaporate platinum, we do the annealing step, and then we remove the excess platinum from the surface. This gives us about 30 nanometer of platinum silicide. Then we use a sacrificial layer here, silicon dioxide, to create about 50 nanometer gap, followed by the position of gold electrode or any metal. We currently use gold, but we want to change to different metals later on. You can see on the SEM the cross section here with the silicon. Then we have this thin white rim, which is the platinum silicide, the 50 nanometer silicon dioxide, which will be removed in the last step, and then the gold electrode. And we use a buffered HF solution at the end to release this structure. And the holes here are, of course, to shorten the time in the BHF. Fabricated structures are shown here, where we have very many different types of lengths and hinge regions. We often see the platinum silicide as a thin white rim around, and we see the air gap here. Then a close-up of the contact region is shown here, where we can see again the silicon in between, then the surface layer of platinum silicide. The air gap is now free, there is no silicon dioxide left, and then we have the gold, and we see how conformal the defects are imaged in the gold or in the subsequent layers. Also, the tip apex is kept round on purpose to try to minimize the contact area. The electrical characteristics are quite good. Actuation voltage is close to what we designed, and pull-in voltage below 10 volt has been achieved with very good overdrive capability. So even with more than 10 volt overdrive, we have a reasonable pull-out and no further problems. To actually test the stability, the robustness, we went to 40 volt with such a switch, and we see that we need nearly 4 times the pull-in voltage until the structure breaks in a destructive manner, which proves again that the design offers a huge advantage in terms of robustness. Then the on resistance in these switches is mainly given by the platinum silicide rim, which is all along this structure, which is rather long. So currently we are in the range of about 4.5 kilo ohm for such a switch, and we obtain very uniform and ohmic behavior over a large range of drain voltage values. Of course, the testing is a bit problematic because in a real application we would have a capacity float, and here we just measure it with a parameter semiconductor parameter analyzer. So we always need to keep the current levels low enough so that we don't incite welding. Then the switching time is shown here. Basically what you see is loaded capacitance, and the time T1 is the time when it starts unloading. That's the time when we close the switch, and this is in the range of 130 nanoseconds, which is corresponding to simulations. So 130 nanoseconds for a 30 micron switch, and we expect that the switching speed is also increasing when we scale these devices. Then we have made efforts on e-beam ridden structures. Here is an example. This device is 3 microns long. the actuation gap is actually ridden with E-beam directly, so it's much larger than what we want to achieve later on. But you see here one of the problems we are currently facing with the platinum silicide. The platinum silicide at low drain voltage tends to have kind of a non-ohmic contact behavior, and it has a bit the signature of a barrier layer. And only once we increase the contact voltage, so the drain voltage, to something like 1 to 2 volts, we can break this barrier layer. And then once it's broken, we obtain the ohmic behavior of the switch. Overall, the design is again also working very well, even at this miniaturized version. However, what we see is that the contact is a critical issue. The resistance here, once this barrier layer is broken, it's now on the order of 20 kilo ohm, but this is still given by the very long access resistance of the platinum silicide. So overall, as a summary, I can say that we believe that the MEMS and NEM switches have an opportunity in the More than Moore space, as they bring additional functionality which is not present. The MEMS switch technology, especially for ultra-low power application, we expect to have an impact. Then we have proposed a new design and also shown the optimization and fabrication for such a device. And finally, I need to point out that to make this work, the contact reliability is really the critical issue. And that's where our work is currently focused on. So I would like to thank our sponsors from the EU 7 Framework Program. You can also visit our website from NEMIAC project with news from all the partners. And of course, I would like to thank my collaborators at IBM for the help with this work. So thank you, and I'm happy to answer your questions.